Hi everyone, and welcome to another Mathematics and Higher Physics seminar at Physics Latam. Today we are happy to have Catherine Cannizzo. She received her PhD in 2019 at UC-Berkeley, currently a postdoctoral scholar at Berkeley. Previously, she was a visiting assistant professor at the University of California, Riverside, and a research assistant professor at the Simon Center for Geometry and Physics at Stony Brook University. His interests are symplectic geometry through concept-based homological mirror symmetry conjecture, as well as Fukaya categories of Landau-Ginzburg model. And today, she will talk us about that a little bit, the geometry of Landau-Ginzburg models and homological mirror symmetry. Thanks for accepting our invitation.
Thank you very much for the invitation to this great seminar. I'm very honored to be invited. So yeah, I'll be talking about the geometry of Landau-Ginzburg models and homological mirror symmetry. So to start out with some motivation for mirror symmetry, its origins in string theory, how do we unite the theories of quantum mechanics and gravity in general relativity? This is kind of an overarching question. Some theory that would unite the two and on small scales agree with quantum mechanics and on large scales agree with general relativity. So the conjecture is that one theory that would do this is if even smaller than quarks, they are made up of strings that are vibrating in space. We have 4 dimensions around us, 3 space and 1 time. And for this theory to work, the strings would have to move in 6 extra dimensions. So the kind of example I like to give is if you take a loop like this and you're far away, you would say, oh, well, that's 2-dimensional, you know, it's a closed loop. But as you zoom in, you see there's actually a 3rd dimension here. So that's kind of an example of an analog of how these 10 dimensions could be, even though we don't see 6 of them. So they would have to be wrapped up very compactly in what's called a compact Calabi-Yau manifold. So I wanted to just ask the audience if you could do like a yes or a no or a thumbs up, a thumbs down. Are you all comfortable with the definition of a Calabi-Yau manifold? Have you all seen that before? See a couple thumbs up.
I think there have been plenty of talks about Cannizzo, so hopefully everyone is familiar.
Well, I apologize for the review in that case. Maybe I should skip over it some. So, yeah, maybe I should actually skip this slide.
It's okay. It's okay. There's no rush. Maybe you can cover it. Yes, it's fine.
Okay. So a manifold, I understand you all got this earlier in the year. This is a way to quantify some different types of geometry. So it's a smooth geometric space of a particular dimension n, the same n everywhere. You have local charts modeled on Rn, and your transition functions are smooth. The Calabi-Yau manifold comes from 2 people, Calabi and Yau. So Calabi had a conjecture that if a manifold can be deformed to be flat, then it emits an actual metric in which it is flat. So what I mean by that is that topologically, if this class C1 of X, the first term class, is 0, then within that class, you can actually find a metric which has Ricci curvature 0. A metric is information on a manifold that measures distance. So like in Rn, it would be the absolute value. And then Yau proved this conjecture to be true so that you can find these metrics. So that's why they're called Calabi-Yau. Some examples, a cylinder, a torus. So we'll look at mirror symmetry for these. And this idea of flat, they can be constructed from like a piece of paper. You could roll it into a cylinder. Whereas, for example, a sphere, you can't do that. And that one's not going to be Calabi-Yau. All right, so this is just a cool picture from Wikipedia. Maybe you all have seen before. This is a higher dimensional manifold, and a 2D slice of it, of this Calabi-Yau, looks like this. Okay, so how do we start to talk about mirror symmetry with this picture? Well, the origins in string theory, we want to look at how can we measure the physics of strings? How can we measure as the string moves, how do we capture its physics? So this is done with a sigma model. A sigma model is a state of the string, and it's a map from a two-dimensional surface. So like the cylinder, which is S1 times R, to the target here. So this is the Calabi-Yau manifold. That's the 6-dimensional extra dimensions where this string is vibrating in. So at time t, what this is telling you is where that string is at time t. So as t moves along in time, the string is kind of moving around and tracing out its movement in this Calabi-Yau manifold. Then mathematically, how you measure that movement is to integrate the energy of this. So you take the derivative of this map squared and you integrate over all of the states, all of these sigma models. Strominger, Yau, and Zaslow, or SYZ for short, wrote this paper, Mirror Symmetry is T-duality. T-duality is the process that produces another manifold that has the same partition function. So X and Y, there are pairs of manifolds, different geometries, different manifolds, but they have the same partition function. The physics of this string is the same. So not only do these X and Y have the same partition function, but actually their geometric structure is mirror. So the complex geometry on X mirrors the symplectic geometry on Y. And I hear that you had some of the original people who discovered this speaking in your seminar. So that's very, very cool. Deloso and Candelas. Okay. So what is symplectic geometry? A symplectic manifold is even dimensional, smooth manifold, and it comes with a closed non-degenerate 2 form called the symplectic form. Within the category of symplectic manifolds, you say that they're equivalent if they're symplectomorphic. A symplectomorphism is a diffeomorphism phi, which preserves this 2 form. So phi pullback of omega is equal to omega. Okay, so some examples. Any 2-dimensional manifold, any surface with an area 2 form is a symplectic manifold. Phase space, if you take R2n and you have position coordinates and momentum coordinates, that is also a symplectic manifold with dp wedge dq summing over j equals 1 to n. That's also a symplectic manifold. Okay, so just to give you an idea of kind of what is symplectic geometry, what are some properties of it. One thing is something called Gromov's non-squeezing theorem. You can't squeeze a sphere into a cylinder. If you have a map from a sphere mapping into a cylinder, its radius has to be at most that of the cylinder. So there's this is sometimes referred to as rigidity. There's some constraints, like a smooth map, you could do a lot more, but a symplectic map has to preserve some sort of like volume. Also, although a symplectic manifold might not be a complex manifold, its tangent space always admits a complex structure. So between the symplectic form, a metric, and an almost complex structure, if you have two, that actually determines the third one. So if you have a symplectic manifold, you have omega, it's a manifold, so it always admits a metric, then you always have an almost complex structure. So this is something that squares two. Minus the identity, it's like generalizing square root of -1. I squared is -1. This is something on the tangent bundle, which squares to minus the identity. Okay, how are we doing so far? Any questions? How comfortable are people with what I've said? Maybe you could do like a thumbs up or thumbs down. See a few thumbs up. All right. So let's look at the other component of mirror symmetry, which is complex geometry. A complex manifold is like a real manifold, but charts are modeled on open sets in Cn instead of Rn. And now your transition functions are holomorphic instead of smooth. So I said earlier that the complex geometry on one Calabi-Yau mirrors the symplectic geometry on its mirror, which is this T-dual. And to illuminate that a bit more, let's consider a two torus. So surface with one hole. And the T-dual of a two torus is another two torus where one side length is inverted. So let me say a bit more what I mean by that. So this is illustrating this mirror symmetry slogan that the complex geometry on X, that means it comes with complex coordinates, X plus IY. If you have X and Y, this is X plus IY is this point here. That should equal or be mirrored to, in some sense, I'd like to illustrate the symplectic geometry on the mirror, which remember, that's when you have a two form that's closed and non-degenerate, so like an area, something that you can integrate to measure area. Okay, so this picture here, so I've been talking about a two torus, and I'm drawing here this rectangle. How we get a two torus from the rectangle is by identifying opposite sides. So just looking down here, we have this square. It has length R1 and R2. I've put these as the same color. So these that are both green get glued, and now we have a cylinder. So this R1 now has become these two circles here. And then we identify the two that are red. So now we're sort of bending these down. And this is the torus, or sometimes it's called a genus 1 surface, the genus being the number of holes. This process of T-duality, what it does in this case is it inverts the length of this side. So this R1, I'm saying the length of this is R1, the length of this is R2. When you take the T-dual here, Now the length becomes 1 over R1, and the other one is still R2. So let's look at the complex and the symplectic geometry of each of these. X, which is when the lengths are R1 and R2. Well, I said a surface with an area form is a symplectic manifold. So the symplectic geometry is encoded in the area. So area of this is R1 times R2. That's the symplectic geometry of this. The complex geometry encodes what happens when we multiply by I. So this is rotation by 90 degrees. There's a scaling that happens. Length R1 goes to length R2. So we're multiplying by R2 divided by R1. So symplectically, the quantity on the first one is R1 times R2. The complex geometry is R2 divided by R1. Now let's look at those same quantities on the T-dual, where we've inverted one side. Now the area is this side length times this side length. That'll give us this area. The area is R2 over R1. And to rotate by 90 degrees, now we're multiplying by R1 times R2. So the symplectic geometry of this one is actually corresponding to the complex geometry of the T-dual and vice versa. Complex geometry here is corresponding to the symplectic geometry here. So hopefully that that provides some kind of like motivation to make it believable that why the complex geometry and symplectic geometry should be mirrored to each other under this T-duality. Any questions about this T2 example and exchanging the two geometries? Okay. All right, so I'd like to do a recap of categories in cohomology, because if you recall in the title, there's this homological mirror symmetry. So far, we've talked about more the geometric mirror symmetry. And I'd like to get to the homological part, and this is the background, the language that we use to talk about that. So definition of a category. Have you all seen categories definition? Yes, yes, okay. It's a set of objects. I'll call them LK, L sub K. It's a set of morphisms or maps between L1 and L2, denoted hom of L1, L2. And it's just an arrow. It's a way to assign something to two objects with the property that you can compose two arrows. Given two arrows, there exists an operation called composition of given two morphisms P1 and P2, you can compose them and get another morphism. So a collection of objects, collection of arrows, and you can combine two arrows. Cohomology is something encoding more the topology of the space. So cohomology theory consists of a co-chain complex. This is a bunch of abelian groups indexed by the integers, so C sub k, C superscript k, and in between them you have differentials, D superscript k, which compose to 0. Sometimes we say D squared equals 0. Oops. If we drop the index. So we have these abelian groups, we have maps between them, and the image of this map is in the kernel of this map. In other words, the squares to 0. The cohomology measures how much of the kernel is actually, how much of the kernel of this is actually not an image of this. We say how much is it not exact? Exact would be if kernel was equal to the image. So the cohomology is the kernel of dk quotiented out by the image of this previous map. All right. So the Fukaya category is actually very geometric. Remember, a category, we need objects and we need arrows between them. The arrows, the morphisms in the Fukaya category, are a cohomology theory. That's why I wanted to do a reminder about cohomology called Floor cohomology. So the Donaldson Fukaya category of a symplectic manifold Y, this is an algebraic invariant associated to a symplectic manifold. The objects of this category are submanifolds. There's certain submanifolds called Lagrangians. They're half-dimensional, and the symplectic form vanishes on them. So like a surface, anything one-dimensional is a Lagrangian. If we're in R2, the axis, one axis would be a Lagrangian. You have dx wedge dy, and you look at where x is 0, then that symplectic form is 0. Given two objects, given two Lagrangians, I need to tell you what the arrow is between them. And the arrow is a cochain complex generated by the intersection points of the Lagrangians. So this CF here is the cochain complex generated by intersection points L1, L2. And since it's a cochain complex, I need to tell you what the differential is. And the differential is very geometric. So as I walk through this, let me just draw a picture which may be helpful to look at. I'll call this L1 and this L2. Okay, so there's a lot going on here. Let's unpack this. Two Lagrangians, if they intersect transversely, so this means that they intersect in a way that there's no redundancies, so that like L1 is not equal to L2. Then we can write down this Floor cochain complex. So this is the cochain complex. And remember, I had these CK. I won't talk about this grading in detail, but there's a way to index the points so that the kth graded part is only those intersection points which have index k. We look at the direct sum. So if there was, say, two intersection points, we'd have C2. We look at all of the intersection points of L1 and L2. And for each one, we have a copy of C. The differential, remember, it's so it goes up in degree. So we have degree J going to degree J plus 1. Given an intersection point here, it maps to this long thing, which I will say more about. This is the infamous Gromov-Witten invariant here. This is a moduli space, which I will define on the next page. This object here is a number. So this is like a number that we count, 1, 2, 3, 4, 5, and we multiply it by intersection point Q, and then we sum over all two homology classes, and we only count index 1. Okay, so this doesn't make much sense until I define what this moduli space is. So let me do that. This is a moduli space. It's a set of points where each point in this set is actually a map from a strip. So this is R cross 0, 1 into the symplectic manifold Y. And all of these points together, thinking of each map as a point, all of the points together actually have a topology. There's a way to put a metric on the set of these maps, and in fact, a manifold structure. So specifically, this moduli space consists of points where each point is a map from the strip into Y that satisfies a bunch of properties. So this one here, this is saying that the area, so we have, this is typically the picture drawn. We have this map U, this is Lagrangian 1, this is Lagrangian 2, this is sitting inside of the symplectic manifold Y. And this condition here is saying that this U has finite energy or finite area. It's the energy is equal to the area whenever this condition is satisfied. So let me just go in the order I have written here. The limit, as you go off to positive infinity, so here's positive infinity, it limits to one of the intersection points, P. The limit as you go off to negative infinity limits to another intersection point, Q. And the sides map onto the Lagrangian. So sometimes you'll hear the words Lagrangian boundary condition. We're saying that this boundary of the strip maps to L2, and this boundary of the strip maps to L1. And the interior of the strip is mapping between the two. Okay, this condition is very important. This is what we call, what makes it a J holomorphic curve. If you recall, I mentioned earlier about this almost complex structure. We can't talk about a holomorphic curve because a symplectic manifold might not be complex, but its tangent space is complex. So we have this J holomorphic or pseudo-holomorphic curve that we can talk about. And last but not least, we quotient by an equivalence relation where we don't really want to count the U, we want to count their images. So we quotient by reparametrization under translation. So if this, we reparameterize this strip by translating it, then it's the same element in the moduli space. Okay, so the cool thing is, if we only consider index 1 strips, I haven't, again, defined for you what index is, but it is to do with how the Lagrangians move along the boundary and kind of encoding how much they wind. If we only consider index 1 strips in this moduli space, that means that this set here, this lots of conditions here, that set actually has a structure. Not only does it have a topology, but it's actually a compact and it's a manifold that's 0-dimensional. So it's a finite set of points that we can actually just count that number. That's what was going on up here. That's why we can count this number. So the differential in an input, if you have an input of P, you count curves that map between P and Q. It's compact. If you think about compact, sequential compactness, if you have a sequence of points and it's limiting to another point, if that limit is in your original set, you're compact. And it turns out that that is true when we count index 1. if you have a sequence of maps U, it converges to a map that's already in here. You don't get anything new that you have to compactify or add in. For other moduli spaces that show up in the Fukaya category, you actually do have new configurations. You have they're not compact. You have to compactify them, and that actually produces the algebraic relations in the Fukaya category. So I won't say as much about that unless I get questions about it. Yeah. So are there any questions? Maybe this is a good time to stop and ask.
Which reference would you recommend for this part?
Let's see. I would recommend for this part, a good reference is through 13 beginners guide to Fukaya categories. This was the reference that I learned this from in graduate school. Yeah. You sum over all Q's different from P in the interception. Yeah, exactly. Exactly right. Sometimes even it could be the same P. Q. So I used a different variable here, but we'll actually see an example where Q can equal P. So, but yeah, that's exactly it. So another way to write this number, when you take the differential of P and you look at the coefficient on Q, it's this count of curves, moduli space. So you sum over all Q's here, and sometimes there's overlap in the intersection points here, and sometimes you have the same point. Yeah, good question. Are there other questions? Morphism is the map in the bottom. Yeah, okay, so the morphism, so the morphism is the cohomology theory associated to this. So it's equal to cohomology associated to, so Hom in the Fukaya category of L1, L2 is equal to the cohomology of this Floer cochain complex with this differential. So this map on the bottom, this map here, that's the differential part. If you remember when we had, let's see if I can up here. We have these, we have these differentials and we quotient, we take the kernel modular of the image, then that's that quotient is forms the morphism. So the morphisms are actually graded again by this case. Yeah, for Francisco.
So I have a couple of questions. So the first one, I guess, so this defines, I guess, a cohomology theory. Is there anything interesting at looking at the homology you get from this?
Oh, that's a good question. I believe this is related to an area of research called Fluor homotopy theory, looking at what theory would have the cohomology given by this. I say cohomology because the differential increases the degree by 1, and homology it would go in the other direction. So that would be if you're decreasing the degree. But you're right, cohomology is generally the dual of a homology theory. Here, there's actually, it's not it's not obvious what homology theory it's the dual of. That's kind of like an active area of research.
And the other question that I have is the one you were not going to mention that someone asked, because now I'm curious, is what do you mean by moduli spaces inside the Fukaya category? Or
Oh, like
yeah, that part.
this part?
Yeah.
Oh, yeah.
So what do you
So
mean by the other ones? The other moduli spaces?
yeah, that's a good question. There's a little bit more to the story than I said here with categories. There's actually a fourth condition, which is associativity. So if you compose two morphisms, I don't know why I wrote it over there. If you compose two and then you do the third, that's the same as if you do P2 and P3, and then you compose it with P1. If we think about this category, it's not immediately obvious what that means. So I'll say a little bit more about this below, but the differential, okay, this goes from a cochain complex to a cochain complex. If you compose two morphisms, so I'll call that operation dot, that means that you have two intersection points. And then the output is the intersection point because you're composing two morphisms, and morphisms are intersection points. So in the way that the differential counts bigons, composition actually counts triangles. If you input two intersection points and you want to find the coefficient on the third intersection point, you count the triangles between the three. So associativity actually comes from compactifying, counting index two disks. That could be this could basically be a talk in itself, talking about the algebraic relations in the Fukaya category as compactifications of these disks. But I think the thing to keep in mind is in the Fukaya category, associativity comes from compactification of another moduli space of disks. I'm not sure if that was illuminating.
Yes, it was. Is the reference you mentioned also talk about this? This is really interesting.
Yes, yeah. This reference does talk about that. Let me see if I can just okay, here and Maybe I can just show a quick picture of this happening. Okay. So I'll just really quickly show a quick picture, if that's okay. Well, okay, maybe I won't. But yes, page 20 is, I'll put page 20 is one. I really like these because it's a geometric picture that you can see what's happening. Another one is page 18. So these are some examples of some of the relations that come out of these compactifications.
Thanks a lot.
Yeah, sure. All right. Awesome. Thank you for the questions. Okay. Okay, so now we know a little bit about the Fukaya category. Let's think back. We're talking about mirror symmetry. The slogan is we have a pair of manifolds, one, and then it's T-dual, and we're saying that symplectic geometry on one is mirrored to the complex geometry on the other. And I've given now hopefully some insight into the algebra encoding the symplectic geometry. What about algebra encoding the complex geometry on the other side? So this uses sheaf theory. Have you all seen sheaves? Thumbs up, thumbs down. I see Eric. Eric has their thumbs up. Okay, see some. All right. The way I think about sheaves is sections of vector bundles. So given a topological space, X, a sheaf is a data of, for every open set in X, you assign a ring, which we can think of as sections. So sections of a vector bundle over an open set. If we have one open set inside of another, then we have a restriction map of sections on V restricting the sections on U. If if we have a covering of U by open sets UJ, and we have two sections S and T, which are equal everywhere on the covering, then they're actually equal on U. And similarly, we can glue. So if we have a collection of sections, Sj on the Uj, and they're equal to each other on overlaps, so maybe this is Uj and this is Uk, and they're equal on the overlap, then actually they glue to a global section, which restricts on each Uj to the original Sj. A quasi-coherent sheaf is a generalization of a coherent sheaf. So a coherent sheaf is when you have a sheaf which is almost a vector bundle. So this would be a coherent sheaf, means for all open U, there exists a resolution with a finite set N and Z, so that the sheaf is a direct sum of what's called a structure sheaf of n times. All this to say OX direct sum n, you should think of this as sections of the trivial bundle X times Cn. So we're just talking about n holomorphic functions. This is corresponding to the trivial vector bundle. quasi-coherent sheaf is a little bit more general. We allow a resolution. We have generators, and then we have relations between them, and there could be infinitely many. So, okay, what are some examples of these? One is what's called the structure sheaf. This is the data where to each open set OX of U, that consists of the functions on U. So if we're talking about a complex manifold, it would be the holomorphic functions on U. Another example is kind of with this intuition of thinking of them as sections. Take a line bundle, L. Then this notation here, gamma of U comma L, is saying sections over the open set U of the line bundle L. That's the sheaf consisting of sections of L over U. A third example, more to the point of this quasi-coherent bit, is a skyscraper sheaf. So skyscraper sheaf so this is defined to basically only see the point Z naught in X. Z naught is a point in X. And the skyscraper sheaf just gives you back C if your open set contains Z naught. If it doesn't contain Z naught, you just get 0. So it's, I think, called a skyscraper because it's sort of like there's a very large amount of information, like a skyscraper, happening at the point Z naught. Everywhere else, any open set not containing Z naught is 0, and then for open sets containing Z naught, you get a copy of C. Why is this example of a quasi-coherent sheaf? Well, it has the resolution by the structure sheaf. In other words, a resolution is a sequence where this is exact. A resolution is an exact sequence. In other words, if you think back to this chain complex, the kernel of one map is equal to the image of the other. It's not just that it contains the image, they're actually equal. If you multiply, okay, let's take functions on X. And any holomorphic function on X. If we multiply it by Z minus Z naught, so if we have a function and we multiply it by Z minus Z naught, does this new function vanish when Z equals Z naught? What do you think? Let's say F was like Z times Z minus Z naught. When Z is equal to Z naught, what is that equal to? Let's see. Maybe I can. So OX goes to OX goes to OZ naught goes to 0. Yes, 0, right. So let's say we had f of z equals z squared. This would map to z squared times z minus z naught. If we evaluate this, so evaluate at z naught, we just get 0. This becomes z naught minus z naught. This becomes z naught squared. You just get 0. So this is exact because everything which vanishes when you evaluate at z naught is exactly in the image of this map. So this is a valid resolution of the skyscraper sheaf. So the skyscraper sheaf is quasi-coherent sheaf. So it is included in those objects. Any questions on the definition of a sheaf or these examples and the skyscraper sheaf? All right. Okay, so why did I introduce these? Well, they're the objects in the category that we associate on the complex side in mirror symmetry. DB-co, which is referred to as the bounded derived category of coherent sheaves. So the co is coherent, the B is bounded, and the D is derived. We saw the Fukaya category. That's the algebraic invariant associated to the symplectic manifold in mirror symmetry. The bounded derived category of coherent sheaves has objects given by bounded complexes of coherent sheaves, of coherent sheaves. What this means is bounded complex means that most everywhere it's going to be 0. So we have these complexes, and then at some point we have something non-zero. Maybe up to k plus m, and then it's 0. So this is a bounded complex. Sometimes you'll see the words bounded above or bounded below. That would be bounded above would be if it's 0 at some point above, bounded below would be 0 some point below. And morphisms are morphisms of these chain complexes, which means we would have another chain complex and we would have all these maps in each degree between the two complexes. The derived part is saying if two complexes, if we have a map between them that induces an isomorphism on cohomology, once we do this quotient, we actually want that to be an isomorphism in whatever algebraic invariant we take on the complex side. So we just declare those to be isomorphisms by inverting them. In other words, deriving that category. So morphisms are chain homomorphisms up to quasi-isomorphism. The quasi means actual on cohomology. So meaning those that induce an isomorphism on cohomology are deemed invertible in the derived category. So this category of sheaves and complexes of sheaves and maps between them is the algebraic counterpart on the complex manifold to the Fukaya category on the symplectic manifold. This seems like it could be more tractable if we had some concrete example of what a morphism between a chain complex of coherent sheaves looks like. So let's look at T2 again. Let's see, let me just, I think I wanted to do a break at some point. Maybe this is a good time for a break, actually. Okay, so let's look at some examples of these categorical invariants. Let's take the 2 torus. We can think of as a rectangle, quotiented by identifying opposite edges. Any integer slope curve is a Lagrangian because the symplectic form is a 2 form and a curve is 1-dimensional. So if you have some 2 form restricted to something 1-dimensional, you're going to get 0. If you think about the universal cover. So if this is the torus, we have a map from R2 to the torus, which is quotienting by this equivalence relation where you identify opposite edges. So we can tile R2 in this way and just identify all of these edges. A slope K curve then becomes an integer slope line like this. So if you have two integer slope lines, they can never close up to make a bigone. So the differential is going to be 0 on a 2 torus. So just counting the number of intersection points is the cohomology, because when we quotient by the image of the differential, well, the image is 0. So we just get everything. Looking at, well, how many intersection points are there between slope K1 and slope K2, you can actually count directly. You can look at, this is a modular arithmetic question where you look at what do you need to have 2 points to have the 2 lines pass through the same point up to an integer. And it turns out that for T2, there's K2 minus K1 of them. So we have our cochain complex generated by K2 minus K1 points. So for example, if we take K1 is equal to 0 and K2 is equal to 1, then we see that the red and the green intersect in 1 point. Let's call it P. If we took K1 is equal to 0 and K2 is equal to 2, that's the red and the blue. Well, there's a second intersection point. So even though it looks like there's 2, remember we're identifying opposite edges. So there's actually 2 intersection points. Okay. Another example is if you take a vibration. So the picture is, I'm going to depict C. I'm going to draw C like this. That's a complex plane. And at each point on the complex plane, you attach a 2 torus. So the way that's usually drawn is you actually draw it up here, and you draw an arrow down like this. So at each point, we attach a 2 torus. Then you can take Lagrangians like the ones drawn here, so maybe here's one Lagrangian, in a fiber, and then you can parallel transport it over arcs in the base. So then it's this sort of cylindrical looking thing. That's a Lagrangian in this larger space, this vibration space. And the way in which you move up here based on this here has to do with the symplectic form called parallel transport. So you're moving in a way that's parallel to the space here. Okay, so this was the main conjecture. This was at the ICM address Cannizzo gave in 1994. Not only do these T-dual manifolds X and Y have mirror symmetry from this string theory perspective, but actually these categorical invariants that I've introduced are isomorphic algebraically. So the bounded drive category of coherent sheaves on the complex manifold is isomorphic to this very geometric Fukaya category of the symplectic manifold. This algebraic or categorical part, that's the homological part of homological mirror symmetry. So let's dive into what does this look like for T2? Why should this be true for T2? We start with T2 on the symplectic side. Then the Fukaya category will be Lagrangians that are slope K lines. And the symplectic property of the torus is encoded by its area, tau. So tau is I times omega, which is going to show up on the complex side. And it corresponds to the area of the torus being omega. Okay, the mirror is also a T2. Now, the way that we encode the complex geometry is, what is the lattice that one quotients by? So in other words, if this is C, we're saying quotient by 1 in this direction and quotient by I times omega in this direction. So this quotient process is actually how you define the complex structure. If you're thinking about a 2 torus as a complex manifold, the lattice that you quotient by defines what your complex structure is, what happens when you rotate by 90. All right, on the algebraic invariant, we need to have a notion of what are the sheaves that we're looking at. It's actually a lot can be understood, basically almost all of it, by just looking at line bundles. A line bundle on this quotient means at each point you have a copy of C. That's the line. It's a complex line. So we have this torus, and a line bundle is at each point on the torus, we attach a copy of C. But we have to do it in a way that it's compatible with this action, this lattice action. So if we were to look at the universal cover and we have a copy of C over each point, when we quotient, we have to be able to glue to get something on the line bundle on the torus. So just writing this down now a bit more symbolically to keep track of the information. On the symplectic side, we have the 2 torus, we have the symplectic form, and the symplectic form means the area of the torus is omega. So the area of the torus is omega. That's the symplectic geometry. Okay, and the Lagrangian is a slope K Lagrangian. So if this is R and this is theta, then we have this slope here. The reason for the negative sign is so that when we look at this grading, remember I said there's this superscript K and it has a degree. I didn't define the degree, but both sides have a grading. And in order for the grading to match up on the complex and the symplectic side, there needs to be a minus sign here. That's why the slopes are negative. Okay, so here's slope 0, slope 1, slope 2. And we also have these vertical Lagrangians, which I call L infinity because it's sort of like infinite slope. Okay, on the complex side, we have C, we quotient by this lattice. And now we have the line bundle L, and we look at tensoring the line bundle L. Are you all familiar with tensoring of line bundles? I see no thumbs. I see a few thumbs. Okay. The way I think about it is if you have a section of a line bundle and you tensor, let's say you have a section S of L, and you want to know what is a section of L tensor 2, multiply the section. That's a section of L tensor 2. So in some sense, it is a multiplication of two things. You can multiply the sections together. For line bundles on a torus, we can actually concretely write down what sections are. If you think about a section on the universal cover, it's a function. A section of C is a function, but they have to be periodic. So they have a Fourier series expansion, and these are called theta functions. So morphisms in DB-Co when we're just looking at line bundles, now amount to looking at sections of tensoring that line bundle, and we can write them down as theta functions. So before, when I was talking about dB-co and morphisms of chain complexes and how do we get a handle on that, now we're looking at infinite series theta functions as a morphism in dB-co. Okay, so on this page, we've matched up objects. The claim is that a slope k Lagrangian is mirror to a degree k line bundle. Now we need to look at morphisms. Two Lagrangians have k2 minus k1 intersection points. So Homs on the Fukaya category side are a vector space which is dimension k2 minus k1. Turns out, if you look at a basis of sections of L of the line bundle of degree k2 minus k1, it's the same dimension. If you look at a basis of these Fourier series expansions, there's the same number. There's k2 minus k1 of them. So as vector spaces now, the morphisms also agree in terms of dimension. But remember, in a category, there's also composition. When we multiply two sections, does that match up with multiplying two intersection points? So the intuition for composition comes from generalizing how the differential counts bygones. If we want to look at, see here, there's this, let me just go back up here. There's one P here and there's one Q here. Now we're going to look at the universal cover, and so there's going to be a tiling of the P and the Qs. So actually, there's triangles where this intersection point P is the same. It's three P's, all the same point. It's a triangle that's kind of wrapping around. I don't know if I can draw it. It's sort of wrapping around the torus when you quotient. So if we have two intersection points, we want to count what are all the triangles between third intersection points. So if we look at slope 0, slope 1, and slope 2, and we want to count triangles, there's actually infinitely many triangles. So for example, between P, Q, and P, let's say we want to compose P and P. We have triangles whose output is Q, and we have triangles whose output is P. And there's infinitely many of increasing area. And when we count, we keep track of the area. Okay, so the intuition for composition is multiplying the two P times P counts triangles, analogous to how the differential counts bygones. And the differential here is 0 because between two lines, we never have, it never closes up to a bygone. We can't have that. These infinitely many triangles are mirror to the infinite series of the theta functions on the other side. So a preview of what the idea on the next page is, we have a map of categories, which is called a functor. So it has to say what happens on objects and what happens on morphisms. And if you compose on one side and then you apply the functor, it has to be the same as if you apply the functor to the two things and then multiply them. And that is really the content of HMS for T2. So the Fukaya category of T2 mapping to dB-co of the mirror. On objects, it sends slope k, a slope k Lagrangian to a degree k line bundle. It sends the jth intersection point to the jth section, and it respects composition. So if we multiply two intersection points, count the triangles, and then map to the corresponding section, it's the same as if we multiplied the sections corresponding to the original points. Does the HMS functor respect any additional structure shared by both categories, or is HMS symmetry only a statement of equivalence as categories? Yeah, that's really kind of the big question that a lot of people think about. What else is preserved? Some recent work is looking at automorphisms. So if you have an automorphism, let's say, of dbco, maybe you want to tensor every quasi-coherent, every coherent sheaf by a line bundle. You just want to have this operation where you multiply everything by a line bundle. What does that correspond to on this side? It actually corresponds, turns out, to something called monodromy, which I may touch on at the end. Or even, what about a complex automorphism on the underlying manifold? Maybe even before we look at categories, what if you just have some automorphism of T2 that in an automorphism of dbco? So therefore, there's an automorphism is a morphism of an object to itself. So Fukaya category of T2 to itself, does that come from something geometric on T2? That's another question that people ask. So yeah. Great. Okay, so what is going on with this composition? Well, the differential counts bigons. You have one input, one output. Composition, you compose two morphisms. So you have two inputs and one output. The Fukaya category, if you hear the words A infinity category, you can actually generalize this and input K inputs and one output, and you're counting K plus one gons. So the Fukaya category actually has more to it. So far, we've been looking at the Donaldson Fukaya category, which is when you pass to cohomology on the morphisms. But you could look at things on the chain level. So back to the torus, if we have a slope 0 Lagrangian and slope 1, so we have one morphism. People typically go in this direction, like composition of functions. So it's L0 to L1 and then L1 to L2. Those have the same intersection point here. Then the output is going to be in intersections of L0 and L2, of which, remember, there's two of them. L0 was this one. L2 had a second intersection point. So this was the P and this was the Q. All right. So when we do even also the differential, we don't just count the moduli spaces. We also, for each curve, we actually multiply it by the area of the curve. So in this case, if I have the picture here, let me go back up here. The moduli space of curves that map to this triangle has one element, namely this curve. There's no other curve in that homology class because in T2, it's actually a complex manifold. So there's something called the Riemann mapping theorem, which says there's a unique holomorphic curve mapping to this. So this count of moduli spaces is 1. Okay, so really there's a 1 here. Then we multiply it by the area of the triangle, and we sum over all of the possible homology classes. And all of these have output P. So this whole thing gets multiplied by the intersection point P. Then we have this other output point Q, we do the same thing. By looking at these larger and larger triangles, this is an infinite series. Turns out it's equal to a theta function evaluated at 1. And that's the same thing that shows up when you multiply theta functions. Okay, so just to recap, the moduli space, we're counting curves from a disk into T2 that have Lagrangian boundary conditions given by L0, L1, L2 that are holomorphic. And the picture is this one. So now instead of a bigone, we have a triangle here. This part of the disk goes to this Lagrangian, this goes to this one. So we have these Lagrangian boundary conditions. And in the limit, as we approach these 3 points, they go to the 3 intersection points. Okay, so U is a J-holomorphic curve, and this condition means that the moduli space is smooth for J that are regular, which means that a certain derivative is surjective. Okay, so the kind of conclusion of this is, if you multiply 2 intersection points, you count the triangles, you have this coefficient C1 times P, and then you have the second one, C2. When you multiply 2 theta functions, these infinite series, and you look at what is the coefficient on the 2 theta functions S1 and S2 that form the basis of sections of the line bundle of degree 2, it's the same C1 and C2 showing up. So that's what I mean by respects composition. If you multiply these two and then you apply the functor here, it's the same as if you applied the functor first and then multiply them together. Any questions so far on HMS for T2 and these relating counting triangles and multiplying theta functions? Right. Okay, so just quick summary. Slope J lines on a torus of symplectic area omega are mirror to degree J line bundles. So we attach a line at each point, and as we go around, that is rotating an amount, that C is rotating an amount J. So this is like Z goes to Z J on the C. That's the mirror to a slope J line. Composition matches, you count triangles on the symplectic side, you multiply theta functions on the other side. So this is a paper of Polishuk and Zaslow. Polishuk, Zaslow on categorical mirror symmetry for the elliptic curve. That's what you call a 2 torus on the complex side, elliptic curve, because it's a complex one-dimensional manifold, so it's like a complex curve. This was my first paper into the realm of mirror symmetry when I was a grad student. Okay, so the title of my talk has geometry of Landau-Ginzburg models in it. Mirror symmetry results exist beyond Calabi-Yau. So far we've talked about Calabi-Yau, compact Calabi-Yau is a mirror to a compact Calabi-Yau, like a 2 torus. If you have something that's not Calabi-Yau, so that's not flat in a certain sense, you can remove part of it so that it is Calabi-Yau, get the mirror of that, and then quantify what happens when you add back in the missing part. quantify that on the symplectic side, quantify that on the complex side, and look at the corresponding change in the categories. So in total, in mirror symmetry, there's actually 3 situations that have been studied. The first one was Calabi-Yau. So the 3 cases are based on this first Chern class, which is a measure of curvature. Compact Calabi-Yaus, that's when this is 0, are mirror to compact Calabi-Yaus. This was the original motivation from string theory, where you have this string moving around in a compact 6-dimensional Calabi-Yau. If you have a positive curvature, that's called a Fano manifold, and everything else, so general type manifolds includes those where this curvature is negative, then the mirror now is a Landau-Ginzburg model. In particular, it's non-compact. So a compact Calabi-Yau is mirrored to a compact Calabi-Yau. If you're in positive or negative curvature, the mirror is not compact. So if you have something not compact, your Lagrangians, especially if it's unbounded, your Lagrangians, there's a lot more that can happen. Your Lagrangians can be also non-compact, and then you kind of don't know what happens as they go out to infinity. So to get a handle on that, also attached to the non-compact manifold is a holomorphic function called the superpotential. So this is how I personally think about a Landau-Ginzburg model, a non-compact manifold with a holomorphic function. And I also think about that holomorphic function as a fibration. So a symplectic fibration where the base is C, and then a fiber is, for me, it's usually a torus. A Landau-Ginzburg model also shows up a lot in physics. And so I think it's really cool that it's kind of showing up in this way here. So getting towards the geometry of a Landau-Ginzburg model, why does it become non-compact? And why do we have this function? So let's think about HMS for C star. This is algebraic torus. So there's different ways to draw it. One is like this, where it's punctured at 0, and another is as a cylinder. So let's think about it first in this way. Here's C star, and we have a puncture. And what we do, let me actually make this black. We look at 2 types of Lagrangians. One is ones of a fixed radius around 0. So these are curves in the surface, so that they're all Lagrangian. Another one is the straight line, so RR plus. So we have here maybe L, the outer one R2, inner one LR1, and then we have, so this is suggestively written here with this O that looks like the structure sheaf notation that we had earlier. Okay, so if we look at L, either of the R's, and we look at its intersection with this O, well, there's one point. So let's do R2. There's one intersection point here. Okay. I just realized this is going to go away. I'm going to change slides. Okay. Well, what happens if we want to look at the 2 Lagrangians which are the same? They don't have transverse intersection. So in order to think about that, it's helpful to have a different picture of C star, which is writing it as a cylinder. And so the way I envision this is, imagine taking this 0 and kind of pulling it out. So sort of like a timeline of doing that. Let's take 0, pull it out slightly. So we have this is a infinity. This is 0. Here's the LR1. Here's the LR2. And now everything on the boundary here, everything on the boundary here is out here at infinity. So continuing in this fashion, we continue this process now. These Lagrangians are circles around the cylinder. So now this is LR1, this is LR2, and then we have this one here, LO. Can people see that, how the C star is becoming a cylinder? I'll do thumbs up or thumbs down. Okay. See if he thumbs up. Yeah, so we're kind of pulling out this puncture here, and then we're kind of contracting this down to this circle here. Whoops. Okay. The reason why I wanted to do that is it's a little bit easier to see what to do if our Lagrangians are not transverse. For example, let's say we wanted to find the morphism in a category. You should have identities. You should have a notion of 1 if you have the same object with itself. So if we have this Lagrangian and we want to find Homs of it with itself, we don't know what the intersection points are. It looks like it would just be the whole thing. So we need this transverse intersection. So we perturb L2. If L1 and L2 do not intersect transversely, perturb L2 by an isotopy that preserves this symplectic form, this area preserving. It's called a Hamiltonian isotopy, and it produces quasi-equivalent objects in the Fukaya category. So what we do is we flow by R d by d theta. What I mean by that is we have this vector field with an amount that depends on where we are along the cylinder, R, but it flows in the direction of d by d theta. So this direction, this vector, is R d by d theta. So now this Lagrangian, if we flow once by that, we have this increasing amount that it wraps. So basically the Lagrangian wraps around the cylinder. And now we can more clearly see what are the intersection points of this Lagrangian with its equivalent presentation of it. We have a z's worth of intersection points. So this tells us the cochain complex. If we want to know composition, well, we have to know if we have the Lagrangian and then we perturb it once, and then we perturb it a second time, now it wraps twice as fast. What are the triangles? Again, there's no bigons. On the universal cover of the cylinder, there's no bigons. But we are going to have some triangles. And the cool thing is that the indices add. So I apologize for the typo. This should be a 1. And this is x sub I times x sub j equals x sub I plus j. Okay, so all of that to say that the morphisms of this straight line Lagrangian with itself is actually the algebra C of x plus minus. On the other side, on the complex side, the mirror is C star again. The mirror to this Lagrangian of radius r. So here's the mirror C star. On the mirror side, so this is radius r, at each point we have a skyscraper sheaf corresponding to that point. So the skyscraper sheaf corresponding to the point r corresponds to the Lagrangian circle of radius r. And the structure sheaf on all of C star corresponds to this line r plus in C star. The fact that there's this one intersection point between any Lagrangian circle Lagrangian and the r plus Lagrangian is mirrored to Homs between the skyscraper sheaf and the structure sheaf, which is given a function here, evaluate it at C, that's a complex number. And the mirror to this component of Homs of the L0 Lagrangian. Well, that's interesting. Homs of the L0 Lagrangian with itself corresponds to that the structure sheaf functions on C star are C of x plus minus, polynomials in x. And we can also divide by x. So rational functions where we have power can have divide by powers of x because we don't have 0. So we don't have to worry about dividing by 0. Okay. So have people seen spec before? Spectrum of algebra? I see 1 thumbs up, 2 thumbs up. Okay. It's an algebraic way to go from functions to a space to a geometric space. So this is C star, and this is functions on C star. So spec, it has something to do with looking at prime ideals in an algebra. But it's going from functions on C star to the actual space C star. Okay. All right, so C star is mirrored to C star. There's no holomorphic function here yet. What about, so we saw C star is mirrored to C star. What about if we add in 0? So now we want to find the mirror to C. The mirror is now a Landau-Ginzburg model. So the mirror is C star, but we have a superpotential that is now attached to it. And the role of that superpotential is to prevent some of the wrapping. Functions on C, now we can't divide by x because we have this 0. So in terms of the algebra of functions, now it's C of x. Geometrically, what that corresponds to is on the symplectic side, we have our Lagrangian here. And then we perturb it, so we have a transverse intersection, but now we only wrap on one side. So we have x, we have 1, x, x squared, and we call this a stop. So we stop wrapping on one side. So the role of adding in this function is to, in this case, prevent some of that wrapping. Okay, so let's look at CP1. This is now when you add in both 0 and infinity. Since this discussion is about skyscraper sheaves, I wanted to check if you all are familiar with skyscraper sheaves. You want thumbs up. Yeah, so this is the one where a skyscraper sheaf at a point is supported near that point. So we get a copy of C if Z naught is in U, and we get 0 if Z naught is not in U. What is the difference now when we look at dB of C star, and now we want to look at dB of P1? The difference between them, one difference is that we now have O of 0 and O of infinity. We have skyscraper sheaves supported at 0 and infinity in P1 that we didn't have before. So, you know, if we think about C star as a cylinder, then P1 is what happens when we add in 0 and infinity. So we get a sphere. So union 0 and infinity. In particular, 0 is a limit. As we go out here, as we approach 0, we compactify that. We get this new skyscraper sheaf. As we go out to infinity, we compactify that. We get this new skyscraper sheaf. So looking at the Fukaya category of whatever the mirror to CP1 is, we should similarly see this process of Lagrangians and find a limit of Lagrangians. Okay. So now we have a superpotential, which is Z plus 1 over Z. And the reason there's two of them is one Z comes from adding in 0, and the other term comes from adding in infinity. And the picture of this limiting Lagrangian is, so let's take this here. Okay. We can stretch out, we can continue to stretch out this Lagrangian. So kind of going around like this, and stretching out more until in the limit we have these two ends, and then we come around, and then we go out like this. So the role of the superpotential is to say what's going on in these ends. So the point is these non-compact limiting Lagrangians need to have, oh, I wrote it below, linear ends with respect to the superpotential. Okay, so I wrote it twice. That's why we have the superpotential. This superpotential governs the non-compactness of the ends in that they have to be linear. They have to have this straight line image. Okay. So in conclusion, let me not go through this again. My work looks at hypersurfaces of tori. So we saw the T2 mirror to T2. I look at T4 and higher even dimensional tori and look at hypersurfaces in them. So it turns out that the genus 2 curve, this is the two-hold genus 2 surface, is actually a hypersurface in T4. And it's of the general type, so genus 2 has negative curvature. And the mirror, this Landau-Ginzburg model mirror, is actually non-exact. That means the symplectic form is non-zero. And it's also not Lefschetz, which means that the theory developed for Fukaya category of Landau-Ginzburg models is primarily for Lefschetz fibrations, which are fibrations where you have a singular fiber, and non-Lefschetz is a kind of one step up in complexity of the type of singularity. So these are Abuzaid Aru and Abuzaid Seidel, Abuzaid Smith. These are some of the resources that I build on with my collaborators, Hania Azam, Heather Lee, and Melissa Liu. So the main result is, if you look at HMS for the 4 torus is mirror to the 4 torus, and you get smaller on the complex side, you restrict your line bundles to the hypersurface, then the mirror is actually something that's a bit larger. So a general fiber on the mirror is T4, and it degenerates to something called the banana manifold, I think because it looks like 3 bananas attached at the north and south pole, like this. That's actually the critical locus. Let me add a room here. But that's the critical locus over 0. So this is the Landau-Ginzburg model that's actually mirror to the genus 2 curve. And that concludes my talk. Thank you so much for your attention.